Okay, so a random variable could be discrete if it takes finite number of values. For example, any value like 1, 2, 3, 4, 5, 6, 7, 8, whatever it is. So it should not be a decimal value. Okay, so hence it will be a called as discrete value. For example, the value of discrete random variable will be an exact value. Okay, it won't be something like 3.5 value, right? It won't be something like irrational rational number, but rather something like 3, 4, 5, 6, something like that. Whereas continuous random variable, that is the difference. Continuous random variable will have range of values, which means it could go up, it could have decimal points, it could continue to have 3.1415962 35. So that way it will keep on going. Okay, so that is the difference between continuous and discrete random variable. Now based on discrete random variable, when you um for example, I'll give you example as well. Discrete random variable could be tossing a coin. Okay, if you represent heads and tails in the form of ones and zeros, one is the exact value, zero is the exact value, and then you start repeating the same experiment n number of times, you will get the probability calculations for those. Okay, and that probability calculations will form a bar like structure when you plot it, and the entire area covered by that bars is called as probability mass function. Okay, whereas the same thing, you repeat the same thing but for continuous values. When you repeat the continuous value probabilities and try to plot them, they will form a curve like structure, and that is called as probability density function. The area covered by the probabilities formed using repetition of experiments using a continuous random variable, that is called as probability density function. Okay, that is what these two terminologies are. And then there is another one called cumulative distributive function, CDF. Okay, CDF applies for both of them. CDF here is nothing but if you want to calculate what is the sum of probabilities at a certain point. Okay, that is called as cumulative distributive function here, that also we will see. And same definition here also. If you want to calculate the CDF between any 2 points or between up to 0 to some point, that will be called as cumulative distributive function here. So CDF is same for both, whereas the area of probabilities for discrete is called as probability mass function, whereas the area covered by probabilities when plotted for continuous random variables is called as PDF, probability density function. Now here again there are differences in the mean. Okay, they exhibit difference in the mean, but we are not going to look at what are these differences. For us, we have direct functions, we will employ those. um, okay, so mean is given by summation of x point in, where x, capital X takes the value of x, or small x takes the value of capital X, where small x is small subset of the sample space. Okay, so here it's summation, here it is integration. So if you notice, because we already in the definition we have said that this is going to hold infinite number of values, you see the infinity integration applied over infinity. The least, the negative minimum value could be infinity, highest value could be infinity. Okay, for continuous random variables. Again, we are not going to look at much here, but what the point I wanted to highlight was types of distributions exhibited by discrete random variable. One is called as binomial distribution, another one is called as geometric distribution, again another one is by Bernoulli distribution and Poisson distribution. Okay, but here continuous random variables exhibit uniform distribution, exponential distribution, normal distribution, also called as the Gaussian distribution. Okay, standard normal distribution, normal distribution, they are more or less very similar. And apart from this, there are few more. Okay, like F distribution, T distribution, and all of those we will look at. Okay, so coming back to a quick brief about binomial distribution. Even before binomial distribution, we will talk about Bernoulli distribution. Bernoulli distribution is where you have independent events. Okay, actually there is only one event. You either take a coin, you toss it only once. If you toss the coin only once, that would be a Bernoulli random distribution. The event should be, the end result should be independent. Okay, so either you will get head or you will get tail. It's not like first I got head and after head I will get tail, again after tail I will get head. It's not like that. So these results are independent. Okay, trials experiments themselves are independent, and there are only two outcomes. That is called as Bernoulli distribution. Bernoulli distribution is only when you have two outcomes, okay, an independent trial, okay, and the experiment is done only once. That is called as Bernoulli. But if you repeat these Bernoulli experiments multiple times, okay, then you will get binomial distribution. Bi means two, right? Okay, binomial will have always two end results. Here also the trials are independent, okay, but repeated multiple times. So that is the difference between binomial and Bernoulli. And geometric distribution also we saw. Geometric distribution is where you want to calculate success and how many times success, how many times it will fail before you get the success. Okay, that number of failure events that you count is geometric distribution. For example, a new player, they want to introduce new player in the cricket team, and what is the probability that he'll hit a half century, right? So first match, second match, third match, he may get duck out, or he may score very less marks. Sorry, less scores, right? So that calculation, what is the probability of him succeeding in the very first attempt? That is geometric distribution. Likewise, we had Poisson distribution. Poisson distribution talks about time. For example, if in your call center or if you're working in any support team, how many tickets can you expect to receive in the first hour? Okay, how many tickets you will get in the second hour? How many tickets you will get in the third hour? So those probabilities that you calculate will be given by Poisson distribution. Binomial distribution is calculated using, we already have SciPy library. In that we have a stats module. Okay, so you all you have to do is just call the binomial dot probability mass function. In probability mass function you will provide three different values, k, n, p. Okay, k value, n value is the number of times you want to repeat. Okay, k value is what exactly are you trying to look for, and p value is the what is the probability that you expect. For example, what is the chance of getting 3 6s in 7 rolls? How many times you are repeating the experiment? 7 times you are repeating. And how many, what is the probability you are trying to calculate for? 3 repetitions you are calculating. And for each repetition, what is the probability? 1 by 6. In the first time when you roll the die, the probability is 1 by 6. If you repeat it 3 times, okay, then you'll get the answer as 0.078. So the probability of you getting 3 6s in the 7 rolls is given by this value. Okay, that is how you can calculate the binomial probability mass function. Likewise, we have repeated um, some other values. So here, instead of calculating only 3 times you are getting the 6 side, here we are talking about how many times you will get two. How out of 7 rolls, what is the probability that you will get it 2 times, 3 times versus 4 times? Okay, this way also you can pass. So you can get the probabilities separately as an array. Okay, um yeah. And here we are just trying to calculate the sum. If someone asked you, what is the probability that the egg that you purchased, okay, you purchased a half dozen of x 6x, what is the probability that 3 of them are spoiled? Okay, how will you calculate that? You can make use of here you can just simply pass 3 value. Okay, how many x are there? 6x are there. And what is the probability? 1 by 2. Okay, so this way you can calculate the probability. Just remember top of the head. Okay, and as I explained, cumulative distribution function is part of subset of probability mass function. Okay, cumulative distribution function is nothing but if I want to calculate what is the probability or what is the area covered, sum of probabilities, or what is the area covered by these bars up until this second value, then I have to count 0 and 1. The area is covered by up until point 2 means 0 and 1 I have to count. So cumulative distribution function, okay. So this is again PMF. For cumulative distribution function, you also have CDF. So up until 2 points, if you want to calculate here that what is the cumulative distribution function for uh, repeating repeatedly getting certain side, it could be 1 2 3 4 whatever it is, 2 times out of 7 times, okay. So that you can calculate. So you will get the direct function you can make use of, you will get the values, okay. Is this understood?
Yes, Sadiq. Yes.
Okay. Okay. All right. Moving on. So here also again we have calculated for another example. You can just experiment with it. Okay. And the next thing is, how to understand these binomial histograms? I mean, there is a unique thing about binomial distribution. The uniqueness is that you start repeating the same rolling of dice. See, initially we rolled the dice how many times? 7 times. And out of 7 times we wanted to calculate what is the probability of getting the certain side once or twice or thrice, whatever. And how many sides it has? A dice has 6 sides. So that we calculated. TMF we calculated already above, right? But this was for only one time. This was what we calculated was for only 7 rolls, okay. But what if we repeat this experiment multiple times, like 600 times we have rolled the dice? When a unique thing starts appearing when you repeat the experiment is that the bars initially they were here, okay, somewhere like this here, and they started exhibiting a normal distribution. This bell shaped curve started coming. If you zoom, if you limit this x value from between 70 to somewhere 150 or whatever, it would look something like this. From 70 to 130, if you limit, it starts looking like this. So now we are saying now what we are seeing is the probability binomial distribution, what has happened is has become a normal distribution. So basically any distribution, any experiment repeated over huge number of times, it exhibits standard normal distribution, okay. I will repeat that again. So it could be any experiment, it could be tossing of coin, rolling of a dice, it could be people securing marks, students securing marks, okay. If you, for instance, let's just say 30 students took the exam, certain exam, and randomly some of them passed, some of them failed. But if you allow, let's just say 1 crore students to take the same exam, what will happen is you will start to notice this pattern emerging, okay. um, so same thing happens for irrespective of any experiment that you do, okay. So hence we call it, hence we call this as uh, law of large numbers, okay. Law of large numbers is nothing but if you repeat certain experiment multiple times, huge number of times, then the distribution earlier which were random start to show a normal standard distribution, a bell shaped uh, curve emerges, okay. This is called as law of large numbers, okay. So these probabilities, if you repeat, you will notice that it form a normal curve, okay. And this is not exclusively for binomial distribution. There are some others also that exhibit this, that we will talk in continuous random variable, okay. So this was about binomial random variable. Next was Poisson distribution. In Poisson distribution, what you are doing is, if you want to calculate what is the income traffic, either the network traffic or the number of events happening within a time limit. For example, your lottery system, how many lotteries can get distributed over a period of time, okay, or how many people can win in a certain area within a certain amount of time, then you can apply the Poisson distribution. Here you would need how many people you want to apply it to, which is a list, basically a range, and what is the average rate, what is the average mean rate. Okay, so average, let's just say in the first hour, here we have taken 3.74, but let's just say, for the sake of argument, let's just say 50 tickets came in the first hour. Okay, and we repeat that over a period of values. Okay, here we have just randomly given the values, but this could be time values as well. So if you repeat this, you will get the distribution, and basis on this distribution you can decide how much resources to allocate to handle those tickets. Okay, so this is Poisson distribution. Likewise, here we have calculated value for 4, average value we have taken as 4, but if you keep on increasing the value for even more, for example, here range I have taken 30, but I have passed the value as 5, here pass the value as 10, here pass the value as 15. Initially it started like this, it was a skewed, this we will talk about what is skewness and all of that, but what I'm saying is this distribution initially, when the average rate was low, was on the left side. Okay, as the average value increased, you see again it became normal, standard normal, just like how your binomial distribution increases. If you increase the number of experiments, binomial becomes this type of standard curve which comes in the middle. Just like that, Poisson distribution also started exhibiting the same behavior. Okay, so there are certain distributions like binomial distribution, Poisson distribution, geometric distribution. Again, not Bernoulli, because now Bernoulli has only one experiment. Not Bernoulli, maybe geometric, maybe binomial, maybe Poisson, and maybe other types of continuous distributions. They exhibit this behavior. This is called as law of large numbers. Okay. Again, looking at the geometric distribution, what we have done is, in geometric distribution we calculate how many times you'll there are chances of you getting fail as a result. Okay, before you get the success. If you want to calculate the probability of you getting heads, okay, let's just say you toss the coin, first you got tail, second time you got tail, third time you got tail, fourth time maybe you got head. Okay, if you want to calculate how, when would we get the head in the first attempt, then you can provide the probability for each tossing of coin, and 20 times we have repeated that experiment, so you can make use of, from statistics you can import the geometric distribution, and for that you can calculate the probability mass function, and geometric distribution it looks like this. Okay, notice how there is not a continuous value. Okay, so it initially the probability will be high that you may get success. Because you didn't get success in the first attempt, you may not get success in the second attempt, so the probability keeps on decreasing. This behavior is exhibited by geometric distribution. I mean, these distributions and all of these calculations are used in trading. Okay, how one want to trade and decide on where to invest and how to do. There is something called day trading. Okay, so there they use a lot of these calculations. Okay, is geometric distribution clear? Geometric distribution, Poisson distribution, binomial distribution. So are they clear for you? What you need is, just by looking at the distribution, you must be able to tell what type of distribution it is. That's all is expected from you for now. When we do the data analysis, we will learn even more about each of these distributions. Okay. Okay, next is Bernoulli. Again, Bernoulli can be imported from scipy.stats. Directly you can import the Bernoulli. Here also you are giving the probability as 50%. Now, Bernoulli, as we know, it has only one experiment. Either you will get pass, either you will get fail. Okay, so here what we are seeing is when you toss a coin for the first time, either you'll get tails, that probability is 50%, either you'll get heads, the probability is 50%. Now Bernoulli distribution is usually seen in features where you have only two values. For example, if you want to, bank wants to give out a loan basis on the gender, let's just say a gender is either male or female. For each of these two genders they want to give. Sometimes the success ratio for males, let's just say for the sake of argument, it may not need not be true, for the success rate of males could be high, maybe because usually in Indian system men work a lot, as in men go outside and work, usually women are housewives. Again, for the sake of argument only, that may not be true. Okay, so you will see for male here, instead of 0, you may see male and this bar is high, so this value could be probability 0.8. So what we mean by that is 80% of the males who are taking the loan are paying back. And here, because women are uh, housewives usually, or they do small side businesses only, so their probability of clearing the loan could be low. Okay, so immediately by looking at the distribution, you should understand what distribution it is, what type of values those are. Okay, and how you can do the analysis for each distribution. That analysis we will learn in data analysis. Okay, and again we have certain differences that I have attached here. You can go ahead and learn those differences. Okay, um, pretty much this is what we talked about till yesterday. Okay, today we'll learn about central limit theorem. Now central limit theorem is exactly what we talked about a few minutes back. Central limit theorem is, here I'm rolling the dice, okay, between 20 and 10 times, and I'm taking the value, assigning the values on the y axis. Here the thing what I'm trying to calculate is, let's just say I repeat the experiment. So ideally there are 6 sides for a dice, and n times I'm going to roll the dice, and I'm trying to expect certain side. Okay, so here the certain side is 1. Okay, and n number of times we are going to repeat the experiment. So if you notice, for roll dice I have passed these two values. So I'm expecting how many times, that is 20 times I want to expect a side, and repetition of I mean the sum of the sides. Okay, that is what it is taken here. Okay, sorry. So sum of the, when you roll the dice 10 times, what is the likelihood that the sum would be 20 if you roll the dice 20 10 times? Okay, that is what we are calculating. If you notice, the values are not normal. Okay, the I mean the x-axis and y-axis are not correctly assigned, but don't worry about the x-axis, y-axis. So what we are trying to understand here is, the values, if you notice, the probability is low, it is somewhere on to the right side. That means we call it as a right skewed. Okay, right skewed uh, distribution. But if I increase the number of times, how the experiment, instead of 10 times I'm gonna repeat the same experiment 1 lakh times and calculate their means. Now you see, ideally on the x-axis you are seeing the z-score. Again I will explain what is standard deviation. I will explain in statistics. But these are all these x-axis has standard deviation, and y value consists of how many times the experiment is being repeated. So if you notice, the standard, it became standard deviation. Okay, it became standard normal distribution. So basically what central limit theorem says is, you take any distribution. Okay, you take any distribution or you take any event, you repeat the event. Okay, large number of times, huge number of times. Okay, and their sum, if you start calculating their sum, it will exhibit normal distribution. That's what central limit theorem means. Again, we will look into deep what this central limit theorem is in statistics class. But for now, so this central limit theorem says just repeat the experiment, calculate the sums, and you will get a normal distribution. And when you get a normal distribution, it will exhibit some properties. Okay. Um, so that properties we'll discuss in statistics. For now, if you notice, they have taken a very simple example wherein which they have calculated the mean values. And when you calculate the mu is mean. So you'll get the mean value as 12.4. But if you repeat the same experiment, you may get the mean as more or less plus or minus some value to this. But when you take the sum of all these values, okay, and start plotting, then you will get a normal curve. So where is it used? It is used extensively in data science. Okay, if you want to build a robust model, and we will talk about all this. I mean, why a model is called as a robust model, how outliers play a role in distributions and all of that. But for now, central limit theorem, you just understand that much. That is sufficient for us. Okay, we'll come back to this central limit theorem. And again, we have repeated the same thing for various dice. Okay, if you want to expect two sides. Okay, so notice the curve is like this, and as you increase the number of sums that you expect, the blue one, this 62, or the purple one, if you notice, so it exhibits this curve. Just increasing the number of experiments shifts the mean. Okay, what you are looking at is the mean value has come to this way. It's exhibiting mostly the values of the mostly the values mean values have come to the normal distribution. Okay, and again, whatever is within this box are the probabilities. Okay, and to that probabilities we call it EMF. Is this clear up until this point? Okay, if no answer, I will consider this as understood. Okay, up until this point, whatever we have learned is for discrete random variables only. Now we are going to look at continuous random variable. Now, as we already saw, continuous random variable is a variable that can take infinite values and be within a range, right? So if you notice, it applies from minus infinity to plus infinity. Okay, and we are taking one small example here, f of x. F of x be a function where the if x is less than or equal to 0, then the value would be 0. If x is greater than or equal to 1, then also value would be 0. How you can calculate these 0 values is by substituting this in this function. Okay, let's just say, let me explain this, what this function means. Let's just say um, you invest some money in a stock. Okay, and when you invest some money, let's just say you invest 10 rupees, then that stock after certain period of time will give you 6x into 1 minus x times return. For example, 6 into 10 is 60 into 1 minus 6. Okay, or 10, 1 minus 10 is minus 9. So minus 9 into 60. So the whatever the value is, so that value is the amount of stock returns. That means you are getting a loss here. Okay, 1 minus x. But if you decrease the value of x 0.5, so 6 into 6 into 0.5 is 3. 3 into half is 1.5. So that means if you invest the amount as 10 rupees, you're getting in return something like 3.5 or 3 value. Okay, um, so you just understand like that. So let this 6x into 1 minus x is a function that represents a real world event. Okay, something like a stock investment. Okay, then what we are saying is, if x value is less than 0, if you substitute x value in this entire value will become 0. 6 into 0 or 6 into anything is 0 into anything is 0 only. Or if x becomes 1, okay, then 1 minus 1 is 0 again. 0 into anything is 0. Okay, so let this be a function. For this function we will plot. Okay, we are plotting by taking x values for this function. Okay, when you do that, you will get this plot, normal plot. Okay, and if you notice this on the left side, if you notice, okay, this part. So what we essentially are saying is, for any continuous value, for any decimal value of x between 0 and 1, it could be 0.00001, 0.00025, whatever the values are, all those probabilities will fit in this curve. Okay, so at x is equal to 0, the sum is 0, or the probability is 0. But if you go a little point here, somewhere here, 0.001, okay, so then whatever the curve is, whatever the triangle it forms, right, some triangle it forms here, so that will give the probability at that point. And likewise, if you keep on going, that will give the cumulative distribution probability, okay, of that curve at that particular point. So essentially what we are showing here is, you take any function, you apply the probability, you want to calculate the probability of continuous values like your decimal values, they will exhibit this curve. This is not, this is, although this is looking like a standard normal distribution, but usually it is not. Okay, and if you calculate the area between them, you will get the probabilities. Probabilities are nothing but areas for continuous random variables. For example, we have calculated between two different points, if x value becomes 0 0.6, between any value between 0 0.6 and 0 0.8, then whatever the area covered by this golden color or yellow color bar, that will give the probability of that particular value, that is 0.6 to 0.8. Okay, this is the general behavior for continuous random variables. And this is the entire area is called as probability density. Okay, probability density function, not probability mass function, probability density function. And this value becomes cumulative distribution function. Is that clear? Likewise, you can
Yes, sir.
calculate the probability of x less than or equal to 0.8. Okay, so this, if you calculate the area for this, and you can calculate the area just by substituting here. Okay, so if you calculate the area, you will get the area. So this I a very similar question was asked in one of the interview questions. um, okay, again, that was a, no one will expect you to do this calculation, but rather they will give you some four options to choose. Okay, again, that scenario is rare because everybody knows that these calculations could be tedious, but then again, it's important to know. So in your data analysis, you will get a lot of these curves, okay, to decide which value, what value it is the highest, what value it is the lowest, how the curve is defining the business problem. So all of that you need to know. Okay, so just know that whatever the area that this exhibits, you can just simply substitute those values, upper value and lower value, in this equation, and substitute and get the value. So that will define the probability of occurrence of whatever the at particular point is, or occurrence of that event at that particular point. Okay, next, for continuous distributions, we have lot of types of distributions, mainly the exponential distribution. Here what I like you to do is just understand the distribution, what it looks like. You need not remember how to calculate this and all. Instead, you will get these values when you plot a histogram in your data analysis. you will get the distribution. Immediately you should understand what type of distribution that is. That is what is expected out of you in this class. Okay, just by looking at this distribution, you should understand it is exponential. Okay, you don't have to remember everything. Looking at the distribution, you should tell what type of distribution, what type of transformation this needs, and all of that. Again, we will discuss that in data analysis, but for now just understand. Exponential distribution is no, see, by definition exponential distribution means, exponential means what? It will increase immediately, right? Immediately it will increase. For example, population of earth graph. So population of earth graph, if you notice, there is a interactive graph also. um, so if you see the chart, see, we, as per science, the population was very very low till up until 2000 BC also. Even till 0 AD, the population, world population was in only millions. But only after industrial revolution, the population started climbing. Okay, all of a sudden it increased, right? These type of distributions where you see that the values immediately increase are called exponential distributions. Okay, not only this, even covid cases, right? Covid cases plot, if you notice covid cases also, earlier there were only less number of cases. Okay, so this is a wave, we saw the wave, right? So earlier the cases were low, coming and going, and suddenly when the wave came, the cases increased. See, here the values were in like 646,000, that means 6,46,000. But here the values suddenly were, what is the value here? Tenfold increase. Okay, 4.3 million or whatever, 5.3 million. So these type of distributions where you see increase in sudden increase or sudden decrease, either way, okay, that type of distributions are called as exponential distributions. Okay, you can read a lot about theory. Okay, so you can understand, if you are interested, you can go through a lot of theory as well. uh, Here you have a lot of theory, I will give you the link. But then what I expect you to do is, as a data scientist, because you're not a statistics student, you're a data scientist, you're going to be data scientist and data analyst. For you, the expectation is just read about little bit of properties. Okay, some properties of this exponential distribution. For example, exponential distribution is used to model the time elapsed between a given event. Okay, so if you want to calculate what is the time lapsed for certain events, okay, and how much is the pike in, or the peak value of the distribution, how it is increasing, decreasing, all of that. Okay, so you have certain things here. And again, lambda. So lambda is the key parameter, we call it rate parameter or average, mean average rate. Okay, so that also you can call. Some places it is represented as lambda, some places it is represented as mu. Okay, so whatever the case is, so basically if you notice the function, what we are saying is, how does my x vary if x value is greater than or equal to 0, and if x is less than or equal to 0, it is always, exponential distribution will always be 0. Very simple. If x value is 0, then there is no cases only, right? If you substitute x value here, e to the power of 0 into anything is 0, e to the power of 0 is 1, 1 into lambda is lambda. Okay, and again lambda, we are calculating lambda at x equals to 0, and if x is less than 0, then this becomes 0. If x is less than, greater than or equal to 0, then if x is greater equal to 0, then it becomes lambda. If x is greater than is equal to 0, then you get a very big number, immediately it will start increasing. Okay, so that is the distribution. So for you, don't worry about the mathematics and all of that. Okay, for you, just understand that exponential looks like this. Here it is a negative exponential, you can say. Why? Because all of a sudden it is decreasing. Okay, initially it was at high value, then it started decreasing. So this is exponential, either it increases or decreases. So density we have calculated here. Okay, again exponential, you have direct function. You have to say See, for exponential you have to use PDF, not PMF. That you have to remember, because exponential is applies for continuous random variables. So density we are calculating of the function, how it is decreasing with time. Okay, initially it was very high at 0th second, something like Big Bang. They call it Big Bang theory, where they say the density of matter, it was extremely high. Then all of a sudden it started, density started decreasing, which means the universe started spreading, something like that. Okay, you just apply a real world example to this to understand. So that this graph represents that Big Bang theory. Okay, although the curve will be steeper like this. Okay, but anyway, still fine. Okay, and next is normal distribution. In normal distribution again, where is that name? Yeah, and in normal distribution you will see, again normal distribution we have seen lot number of times. Standard normal distribution is, if you plot the z-score or the standard deviation, you will get a bell curve. If you plot the means of the values, we will again see this how to calculate and all of this in depth in statistics, but for now, for probability class, you just understand, if you arrange the probabilities of all these um, plots, whatever the events that you conduct, it will exhibit this, and plot versus z score, then it will exhibit this normal curve. This will be called as standard normal distribution. Okay, for you, just understand. um, okay, here for example, for you, you can see here, right? Z is calculated. Okay, 0, 2.5, 5.0, all of this. Okay, Z value is nothing but how far away a certain point is from your mean. That is what Z value will tell you. Z score will tell you how far away is the point from your mean. And if you take mean as 0, standard deviation is 1, that means you are telling, by saying mu equals to 0, sigma equals to 1, what you are saying is, for certain event, because you repeated certain event multiple times, the mean value became 0, and it is 1 point away from the mean. Okay, that is what, again we will see this in depth. If you don't understand, it's fine, just understand the plot, what it looks like. So all of these are standard normal distributions. Okay, we have again, to plot this we have norm. Okay, statistics.norm.pdf, so you can get this plot. Again, density of standard normal deviation, standard normal distribution looks like this, which is same as above only. Okay, nothing extra. And if you plot it in 3D axis, it looks something like this. Okay, same thing, just plotted on the xyz plane. Likewise, we have chi-squared also. I will quickly cover this and we will stop. Okay, chi-squared distribution also we have. Chi-squared distribution means, initially it will show this sort of distribution. Initially it will be high, then it will even out as the values grow. Okay, so standard chi-squared distribution is, we have theory here as well. Chi-square distribution is used for inferential statistics. We will see that. And to calculate confidence intervals and hypothesis testing, we will see all these topics in statistics stacks class. But here you just understand that chi-square distribution, it's closely related to standard normal distribution. The moment you see a chi-square distribution, you see a distribution like this. This is also called as left skewed distribution. That means all your values are shifted towards left. Okay, so what to do when you see this type of distribution, we will talk about in statistics class, but just understand this is called as chi-squared. Here the mean of the distribution is k, variance is equals to 2 times the k value. Variance will always be twice as that of mean. Okay, that much you remember, that is more than sufficient for you. Okay, here if you notice the center point here, upper point, it is somewhere here, somewhere at 2.7 or 2.6. Okay, and if you calculate the entire variance for this, it will be more than twice of that particular mean value. Again, f distribution is very similar to chi-squared, but it is again further shifted towards the left. Okay, so where is the f distribution? Okay, t distribution. Again, f distribution is used in conducting of certain tests. We call it f test. Okay, and it is also used in ANOVA testing. We will see what that is, ANOVA testing, how to do, what does it tell, how to understand the various distributions using ANOVA. Okay, we will learn what is degrees of freedom. So all of that we will learn. For now, just understand that f distribution starts like this. Okay, completely starts like this. For this you will do the transformations to convert to normal distribution. Okay, f distribution looks something like this. And likewise, t distribution is a very similar case to standard normal distribution. If you notice, it exhibits standard normal distribution properties. But if you go through the details of this, t distribution has something unique. It is used in understanding the distributions which look very similar. Okay, so it's also called as student t distribution. And if you want to understand the use of this, it basically, if you notice that there are distributions which look very similar, which exhibit normal distributions, then you apply a t test on top of that. Okay, um, so you can read through the definitions. Okay, pretty much you can go through. Here also again, the um, formula or complex, you need not remember the formula. Just understand that if two different set of students scored same type of marks and their average was also same, that is when you apply a t-test to understand what contributed to that behavior and how different they are. Okay, here they measure the means. Okay, means of the distributions, and they apply the t distribution. Here you can very clearly see that this is a t distribution, the curve, and the standard normal distribution is in the dotted line. Standard normal distribution is ending. There is no higher limit for that, whereas t distribution has minus infinity to plus infinity. Okay, so pretty much that's it. And one last one is uniform distribution. In uniform distribution, basically, you have distribution something like this, where one good example would be people earning incomes between certain range. If you start calculating the range, people earning their salaries between 0 to 10,000, 10,000 to 50,000, or 50,000 to 1 lakh, 1 lakh to 2 lakh. So that way, if you start plotting, you will get your uniform distribution. It looks something like this. Okay, so number of people earning between 1 lakh to 2 lakh could be some 60% of them. Okay, so that way you can make out. So again, here they have plotted probability density. You may get values also, you may get the frequency also. Okay, so that this is what uniform distribution looks like. Again, ignore the beta distribution. Beta distribution is a variant of chi-square distribution. Okay, pretty much that's it. Again, Bayes theorem we learned already. I just wanted to show you the example with a calculation. Bayes theorem we learned in yesterday's class, stating that any event that depends on, for example, there are dark clouds and there is a chance of raining. If out of 30 days, if 10 days there was dark clouds and 10 days it rained, okay, then they are dependent events. Then how to calculate the probability for dependent events is given by this Bayes theorem, wherein which you calculate the probability of occurrence of event A given event B, okay, by using this formula. So that we already saw yesterday, it is here. Okay, occurrence of event B given occurrence of event A given event B is given by occurrence of event B given A into event B divided by event B. Event A divided by event B, that is probabilities, not exact events. so that you can calculate. For example, so if you notice the Bayes theorem, so 20% of the time it rained without clouds, and 40% of the time it was cloudy but didn't rain. Okay. um, and 80% of the time there were clouds given rain. Okay, sorry, clouds were there, and rain also happened. And again 40% of the time it's vice versa, so it rained after there were clouds. Okay, something like that. You can calculate the Bayes theorem probabilities. If you understood this much, this completes your probability class. Okay, this completes your probability class. Any doubts, please ask me now.